All right,
Okay.
recording in progress.
Mhm.
And we can see your screen just fine.
Yeah, okay, thanks. So I start. So thanks for this opportunity to introduce this package developed possibly by myself, but also I have quite a lot of comments from my research group and collaborators. So this package is a Python-based package for data analysis in space physics in our field. Before I go to details of this package, I would like to introduce some history of this. So first, about the motivations, I probably first want to learn Python in the beginning. And because it's an open source package, nowadays we have a lot of free packages developed in Python. Those general packages or in those packages have been developed in our community. For develop this package, I would like to create a standard framework for data management, aiming to manage many kinds of measurements or observational or simulation data in our fields. And I want to combine different kinds of data and make visualization for them. For example, integrated them in a figure or in a dashboard, so that we can easily to check the interesting events with different kinds of view of the data. So actually, part of the functionality of this package were developed when I studied for my PhD before 2016. It was built on MATLAB, and basically it was used to view the SCAT, incoherent scatter radar data, and also the Omni dataset. So during my postdoc work, I start to learn Python and develop several functions based on the Python language. And at that time, those functionality are basically function-based. So they are a set of functions and the data set has been were expanded with DMSP, for example, MS, or give them simulation model results. So since
Oh, excuse me.
sorry.
Before you moved on from the motivation slide, I wanted to just point out part of my motivation for inviting you to the Telecon here today was we had looked through the Python packages that you use to put Geospace Lab together.
Yes.
And it actually includes a lot of PyHC packages that we have on the website already, but you have sort of wrapped a lot of them and you kind of have a higher level package wrapping a lot of their functionality.
Yes.
And I thought that this was a particularly good example of ways that higher level libraries like yourself could be brought in to kind of manage the duplicated functionalities we have in a lot of our PyHC packages.
Yes.
Yeah, there's lots of sort of competing ways to do things through various smaller packages, and I like how you brought them together in this one. So I'm looking forward to hearing about that.
Okay, yeah, sure. I would like to introduce more about those details. So
yes.
Yeah.
And also PhD Comics is a wonderful comic strip. That's a good one.
Yeah, thanks. So actually, this package aims to overcome several challenges when we use the data. For example, in space physics, data from different kind of sources or providers, data stored in different file formats, also different data from different providers can be ruled in different ways for the 5 segments. Also, the data, the variable stored in the data file can be depends on one or more dimensions. Even for one dimensions, the variable may depend on one or more variables, and data variables with different temporal spatial resolution. Also, sometimes for most of the measurement, maybe they are evenly spaced, or sometimes there are some gaps, or even there are unevenly spaced data points. And we also deal with a lot of work for different coordinate transformations. So this package aims to overcome those challenges by establishing a standard framework for the data management and visualization. As Sean said, this package is built on the top of several kinds of packages, and it's a kind of high-level APIs. This package is a component of several core modules. First is Data Hub, and then visualization for visualize different data which assigned from Data Hub, and also include the space coordinate system module aims to use a unified format to make coordinate transformation. And it has included a toolbox which mostly function-based, include a lot of functions to make basic Python procedures or some utilities used for supporting the other modules. The package also has a module called configuration, which can be used to set global options and preferences for those core modules by the users. So this the core module is a Data Hub. It's a class-based module which has 3 base classes. I call them Data Hub, Dataset, and a variable. So basically, the Data Hub is the center of this module, which can be used to add one or more data sets. And the data sets is a set of variables, but also included those metadata. The variables record the data arrays for different kind of physical quantity. For example, the IMF, BY, BZ, BX components can be recorded in variables separately. Variables has several attributes like value, which record the data array, and arrow records the arrow estimate of a variable. It also has attributes like name, label, data, group, unit, depends, and dimensions, which supported to record the metadata for the variable. I made them explicitly, not like other data array package, for example, X array or the data model in Astro, because those attributes are frequently used in the following procedures. The variable class also connected to a Vero class, which has a number of attributes to support visualization process. This data hub base classes can be extended. For example, this dataset has two subclasses, which are called dataset user, dataset sourced. The dataset user faced to the users if the user has their own dataset, which can be added into the data hub. Dataset sourced included aim to manage those data has been supported in this package from those data made from different online providers or the local data sites. For example, we have Omni dataset, ASCII dataset, DMSB SUSE dataset, and so on. This data, this value stored in the data array stored in variable class is in the form of nuper array. So basically, any function used in numpy can be applied to this data array. This data hub class uses this method called dock to dock any dataset we want. It's something like the space station that the data hub is a core module of the station, and it can dock different kinds of datasets. Those datasets are different living module or empirical module, which can be added in this core module. Those variables can be different kinds of devices inside a module. So with this object-based design, we can manage many kinds of observational and simulation data independent from their dimensions or attributes. In addition, those attributes or metadata are also stored in the dataset as a variable or dataset objects. So the user can also quick check those attributes by looking at those objects. So to create this, to dock a dataset is quite a simple process in GeoSpace Lab. Basically, we only need to define the time window we want to dock and to specify the source dataset. For example, here we define the start time and ending stopping time for data hub object, and then we dock the Omni dataset by with several inputs. This data source contents control which dataset we want to use. This content can be looked up by using a function in the data hub. I could show that later. So for Omni data, they also require several specific inputs. For example, which type of the Omni data and which resolution of the Omni data, and some other parameters. So this package aims to dock those datasets automatically for most of the cases, and the data array it should be independent from those file segments. So in the background, the the dataset class will search all the data files that associated with the time window and clip the time window and get the required data. After docking, the variables can be retrieved by by this kind of format. So the dataset object is a kind of dictionary, and the variables can be assigned from the key and the values of the dictionary. The data hub is basically it's manage the data. I also create the visualization module to combine to cooperate with the data hub and make a quick look of the data that docked to the data hub. The visualization module has three basic classes. They are figure-based, dashboard-based, and panel-based. What that means, so if we look at this schematic figure on the right side, so the figure is the outer boundary of the figure, and I divided the figure into several dashboards. The dashboard control several panels within the dashboard. So the dashboard can set the layout of those panels. Each panel can be 1D or 2D plots, which depends on what kind of variables inputted in this panel. So basically, this visualization module so far it's developed based on the matplotlib package. So most of the plot routines supported in matplotlib package can be used in this visualization, can be used with the visualization module. This dashboard class is a kind of it has been combined with data hub. So based on that, there are two main subclasses were developed. One is the TS dashboard, which manages the time series plots, and this GL dashboard, which manages the GL mapping or map projection in the geographic or geomagnetic coordinate systems. So for time series dashboard, it can be added with several panels or time series panels. Each panel will show the time-dependent plots of the data. For the GL dashboard, it mainly shows the mapping, map projections in different coordinate systems. Based on the two subclasses, we have developed, for example, SCAT dashboard, aiming to make a quick look plot for the SCAT incoherent scat radar data, OMINI dashboard for OMINI data, geomagnet dashboard for geomagnetic indices. For GL dashboard, we have, for example, DMSP SUSI dashboard to look at the SUSI images, GATEM dashboard to look at the 2D distribution of the simulation result, and so on. For the time series dashboard, we have already built in several functionalities. For example, the user can add title, panel labels, and also it has several kinds of marking tools. For example, to the vertical dashed line, shading, or top bars. This time series panel can also automatically detect those data gap. For most of the cases, if there is a data gap which has a longer time window than the time resolution, then the panel class will detect those gaps and make them visible in the figure. Also, since the data has been collected independent from the file segment, the data array can be shown with continued distribution independent of the date. This code shows an example that shows an example to visualize the Omni dataset. You see this, we only need several lines of the code to make a quick look for the Omni data. The process are similar as the first several lines are similar as the code I showed before to dock a data set, and we retrieve variables from different data sets. Using those variables, we can build those time series quick look plot very quickly. For example, here this figure includes 3 panels, and you can just set the layout of those 3 variables in a list, and then use that as an input to the set layout function. And because all the associated attributes of the variables has been assigned into those variables, this time series dashboard or panels can automatically detect those attributes and use those information to set the figure or set in different panels. We can also use different format of this layout to get different layouts of the panels. For example, if we join those variables into a sublist, then the figure will also combine different kind of variable into one panel. If we want to add another panel, that's also easy. Just add these variables here, another variables here in the list, and the third one, fourth one, and the fifth panel with more variables. And since it's independent of the file segment, so it can the time series plot can show data within several hours, or several days, or several months, or even more than 1 year. For this GL dashboard, we aim to make a 2D mapping of different kinds of data. Basically, it's a high-level interface of Cartopy. Cartopy is quite popular package to mapping the geospatial data. However, in our field, we often look at those data in a different coordinate system, especially in a geomagnetic coordinate system. So this geo dashboard or geo map panel has the functionality to make a coordinating system transformation and mapping 1D or 2D geospatial data in the corresponding coordinate systems. Also, those coastlines can be added in another kind of geomagnetic coordinate system. So this geodashboard and geomap panel can map 1D or 2D data in both northern and southern hemisphere. Southern hemispheres. It can overlays with many kinds of 1D or 2D plots supported from Cartopy or Matplotlib. It also has functionality to map this satellite trajectory with time ticks. It can also map the cross-track vectors along the satellite trajectory. Also for coastlines and zonal and meridional levels for the latitude or MLT can be added automatically in different kinds of maps. So this is an example that this GeoMap panel can map the TEC data, for example, here to geographic polar map or geographic latitude local time coordinate system or AAC-GEM latitude and magnetic local time coordinate system. Actually, we can do more creative things to add different plotting style in either the time series panel or geo panel. So, for example, this is this maps the neutral density from swarm satellite or electric density from swarm satellite along the satellite trajectory. The densities are basically 1D 1D data, but we can apply different colors to represent the values of the data. So basically, any functionality in Matplotlib or Cartopy can be adopted, and we can make more fancy plots with GeoSpaceLab. So this is an example that we can use GeoSpaceLab to combine different kinds of data in one figure. So as I show this schematic plots for the figure layouts, this is a complicated figure layouts with 3 dashboards. One is a geospatial dashboard on the top with 2 geo panels, and 2 time series dashboard on the bottom with several panels. So using GeoSpaceLab, we can easily create this kind of complicated dashboard. And we can look at an event with different kinds of data. So we don't need to open different figures that we created by using different routines. They can be just integrated in one figure. So this schematic shows the full view of the classes used in Data Hub visualization and Express. The express basically is some kind of higher level API connected with time series dashboard or geo dashboard for specific data set. We using those express dashboard, we can easily create quick look plots for different kinds of data set, which those dashboards are marked by the yellow colors in the center of this figure. In addition to the other three core modules, I also developed this space coordinate system module. This module aims to manage different kinds of coordinate system used in our field. So far, it has included, for example, geospatial, geographic coordinate system, the local east, north, up coordinate system, AACGM, apex, and so on. Of course, for AACGM and apex, I worked the Python package, which have been developed in our field. Because those coordinate systems have been developed by different institutes. They have different kind of grammar to manage those transformation. So I developed several and also worked several different coordinate system, and it used the same method to make this transformation. For example, to GU means convert the current coordinate system to geographic coordinate system, to AACGM, to apex, and to QD, and so on. I should say this module is not perfect so far, but it has supported the functionality in Data Hub and visualization modules a lot. So if you have some any suggestion can make it better, that would be also very helpful. So far, this package has supported more than 27 data sets from 6 different online data sources or providers. For example, the OMINI data from CDA Vibe, SCAT, or SCAT TEC, or DMSB data from Madrigal database, and also Millstone Hill incoherent SCAT radar. Also include the DMSB SUSI from GHU APL, AMPRA data from GHU PL, and the potential map from SuperDown, and several kinds of geomagnetic indices, and swarm data from ESA database. So these sourced data sites can be expanded in future, and because those base classes like dataset and variables has already become stable to use, so it's not difficult to add any kinds of data set in this package in future. And for most of the sourced data sets, it supports to automatically download those data files from the online database. For example, the OMINI data or those data sets from Madrigal, and also DMSP SUSI data from GHUPL. So some of the online database provide, for example, a Python module that can be used to download the data. For example, the Madrigal web can be used to download any magical data, but of course it requires the input, different kinds of input. Some database, online database were built on FTP, so it can be easily to use a Python package such as FTP lib to download those data, as long as the file format or file name format are known. For some data, for example, GHU DMSP SUSE data, I need to use Python HTML request to download those data. So it requires some strategy to manage those things. But basically, those data sites listed in this form supported automatically download and automatically load. I think this also benefit from those data file names. If they have regular name segments, then we can use, for example, Python Ray or some other packages to recognize those file name patterns and identify which date and which type of the data product, so we can collect those data files using the internal function in the source data site. Also, this package or the classes used in this package can be customizable. For example, for the incoherent scatter radar measurements, we can make a specialized function in their data site. For example, to check and list the radar beams. We can also filter out those beams that we don't want to use, and for example, just focus on the field line beam measurements. We can also make a transformation for the radar data from azimuth elevation range coordinate system to latitude, longitude, height. We can also make a quality check for the radar data. This quality check, of course, for different kinds of data site, the method can be different, but this quality check sometimes is quite important, not only for the incoherent scatter radar data, but also, for example, for satellite measurements and so on. And also, the package has provided several utilities to support dig out the data and the variables in different kinds of data sources. Here it listed several functions to check the data and the variables in the magical database. So for a summary, this package has provided a framework for managing and realizing data in space physics with object-oriented design. It's under the BSD3 cloud license, and the latest version is 0.51.1, so it's still a pre-released version. I wish I can make most of the functionality being stable and make a stable release before the end of this year. So the package has supported more than 27 datasets from 6 online or local databases. It aims to automatically download and load different kinds of data supported in the package. It can make quick look plots especially for the time series and the geospatial data. Due to this objective-oriented design, it is highly customizable and extendable. It's so far due to the source the dataset has been included in this package. It's particularly suitable for event and statistical analysis in the studies on the magnetosphere, ionosphere, thermosphere coupling. So in future, if more data set can be included, I think it's the usage of the package can be also extended to other subfield in space physics, like in magnetosphere or in the solar wind or solar physics. So there are several future plans for this package. First, I should say the documentation for this package is there. However, I probably need to add more details for this documentation to help the users to use this package in a smooth way. Also, there are more observational or modeling data set can be included, and it can be included more specialized functionality for several frequently used data sets. For example, the Omni data set or Swarm data set, and it can include more kinds of plotting styles for the 1D or 2D data. For the moment, it cannot support the 3D visualization, but hopefully in future we can find some better way to present 3D visualization, because Matplotlib does not support 3D visualization very well, for my opinion. And also, the visualization module is based on the Matplotlib and Cartopy. So basically, it produces static plots. How to make those plots interactively show it's also a question for me so far. And there also this package actually is a kind of secondary product from my research work. So probably I would like to search possible funding to support the development of this package, and also I would like to join this PyHC community in the near future. I have submitted a manuscript for this package to the special issue in Frontiers in Astronomy and Space Physics. Just today I got the reviews reports, and it looks like the manuscript can be accepted after review. So I will work for that. So the package basically has quite many dependencies. For example, those general Python packages like Tom, Ray request, beautiful SOAP4, NumPy, SAMPy, and so on. And also I select several specialized packages developed in space physics community. For example, Magical Web, SSC, WS for satellite orbits, AAC Gem V2, GeoPack, ApexPy, and if some others are not listed here, I would add them later. All of the data providers, and I would like to acknowledge all of the data providers and the online data sites, databases that have been supported in Geospace Lab. And I would suggest the users always to check those data sites and get familiar with those data set when using Geospace Lab. And of course, if needed, at least contact the PI listed in the data source the data site for publications and so on. This is a wipe of the package and the documentation link for this package. And so far this package is basically developed by myself. So I would like to welcome any collaboration or contributors in future if you have any suggestions or contributions. That would be very helpful and very nice. Okay, thanks. That's all.
Thank you for that.
Yeah.
I know I have a few questions after hearing that presentation, but I first want to let anyone else jump in front of me if there's any other questions, or I should say any, not other.
I've got one.
Yeah. Okay, please.
I'm quite. I mean, you did that on your own. I'm quite impressed.
Yeah. So actually, I got quite many comments from my colleagues. For example, my supervisors and also the PhD students who are using this package. However, I think one of the limitation to let them join this project, I mean, make them as a developer, is that they are always using the MATLAB for research work. So it's hard to persuade them to use Python, fully use Python and write code in this package. But anyway, I got contributions from others. Second is that actually several functionality used in this package had been developed before when I use MATLAB. So basically, I just translate them from MATLAB to Python. But I think this organization of the data set and the variables are pretty new in this package, and I think it can be a kind of standard processes using in our field. It's quite so far it works very well to organize different kinds of data sets.
Thank you.
Thank you.
I think you should promote this to for a larger ground-based community, ionospheric community. I'm sure they would be pleased to use and contribute to this tool.
I think I would like to do that. Because my working load is quite limited to include more kinds of data sets so far. So if I added more new data set, I would like to contact those PIs and make this package notable for them. I think that would be help.
Thank you.
Thank you.
You got your hand up, Rebecca? Feel free to go.
Yes, I'll choose my top 2 questions
Yeah,
so I don't
please.
take up all the time.
Mhm.
Quick comment. So you could quickly expand the number of data sets by simply using CEDAWeb and Happy as your access points for data. I'll encourage you to take a look at that. But questions would be for your coordinate transformations. How do you treat vectors as opposed to scalars?
So for vectors, actually right now it cannot process vectors. So I make a coordinate transfer basically for those coordinates, not the vector values, but this I have think about how to deal with that. I think with this kind of framework, those vectors also can be also transformed with similar functions.
Okay, I guess my last question is on a similar trend thought. You said you could show coastlines with
Yes.
your plotting tool.
Yes.
Does that account for the rotation of the Earth in non-geographical coordinates, such as magnetic systems?
Yes. For example, this figure shows coastlines in geographic coordinate system and also a CGM coordinate system. It works well. Yeah, I made coordinate transform for the coordinates of those coastlines and map them in the new maps.
Okay, great. I have lots more, but if you want, we could talk over email or something.
Yeah. Okay. Thanks.
I'll put my email in the chat and let you start it.
Okay. Yeah. I see.
I am noticing that we have 1 minute left till the top of the hour. In case anyone needs to jump off the call and had a question, I'll leave room for it now. But I'm cool to stay here for a few more minutes to chat if anyone else is.
Yeah. So if you have any, please, any question?
Yeah. If going once, going twice? No. Okay. I was going to ask sort of a follow-up of what Rebecca had mentioned there before asking her question. Have you looked at all at the Happy project?
Sorry, what project?
Have you looked at the Happy project, HAPI, for getting data?
No, I didn't know that.
Here.
I put the link in the chat for thanks for bringing that up, Sean. Happy will get you time series data from See the Web and a bunch of the other servers in a regularized format. And for time series, it also has a built-in Happy plot that does a lot of what you're doing with the plot. So I think you could definitely use Happy to add data sources to your system and mine it for useful utility.
Okay, that's good to know. I think that's quite useful. Yeah, if I want to include more data sites.
Yeah, data access is always a problem that we're tackling here in this field, and Happy has been one of our favorite pet projects lately for getting data, because you basically just hit a REST API and multiple different data providers can set up their data to just kind of work with Happy servers, and it makes it easy for everyone to play together in the common way.
Okay, yeah, thanks. Yeah,
and likewise, I noticed you had a coordinate model. Are you using the AstroPy coordinate model or rolling your own?
Sorry, which model? No, this is different from AstroPy quality model. I think AstroPy quality model is a kind of subclass from NumPy array. So this is not a subclass from NumPy array. Actually, I add NumPy array as one of the attributes named value here. Yeah, so I didn't use a subclass of NumPy array because that technique is does not working perfectly so far. So there are quite a lot of issues when using NumPy functions, apply NumPy functions to the subclasses. So I'm still pay attention on the developing of that subclassing technique. If it becomes better, I think it would be modified and you use that as for the variable class. Another thing is that because the variable class also include another attribute called arrow. So arrow can be a string or nuclear array. If it's a string, then it can detect the arrow variable stored in the same data set that the variable belonged to, and get that value. Another way is those arrow data array can be stored directly in this arrow attribute. So it's a kind of flexible way to manage the data with its arrows. So if we subclass the data from the subclass this variable class from NumPy ND array, then probably these arrow attributes need to be modified and just assigned with a Python string, and the string is the name of the variable stored in the same data set.
I think I have to drop out now, but thank you for that.
Okay.
Yep. See you, Sandy. Thank you. That reminded me actually. Could I put my email here in the chat and ask you to send the slides to me if you're comfortable with that?
Yeah, of course. Actually, I have sent this presentation to Julie.
You did?
Yes.
Okay, good. If Julie has it, then I can get it from Julie.
Yeah. So probably she will share this presentation in some Google Drive folder.
I really like how many class diagrams you included in the slides. It makes it really easy for a programmer like myself to follow along with what is actually going on here.
Okay, I see. Yeah.
Cool.
Of course, I can send my presentation to you.
Yes.
Yes.
No, I'll just get it from Julie. That's perfectly fine.
Okay.
Lutz, Darren, or Bernie, do you got any questions while you're hanging out here? Otherwise, I'm gonna, I think, turn off the recording and shut this down.
No, I was just looking at all this very interesting package, but we should, I guess, in general, like there's a lot of duplication of effort. Things have been done already and done in a different way. It makes the whole system like very confusing for people. But I think it's very hard for a new person entering the field to know what's already out there. So we have a lot in Komodo. So Rebecca has talked to him, and so yeah. So just so yeah, it's very interesting effort, and yeah, I like the diagrams as well. So it's good to know what's going on.
Okay, thanks. Yeah. So actually, yeah.
So we have been in the Komodo project. We have been using Plotly as the visualization instead of Matplotlib.
Yeah, I was going to mention that because that gets you your interactivity as well as possibly 3D visualization. So
right. So I think Plotly is one of the useful packages and which can be adapted in future. And I have some investigation for that package, and I think it can be integrated with this package. So far I use a Matplotlib because anyway I think the figures, the plotting style and the figure quality is quite good, and the plotting style is quite similar as what we have done in publications. Plotly may produce more modern style of the plots. So anyway, I think that's a good
Well,
option.
it's a very natural migration path, especially if most of your users are currently using, Matplotlib for doing stuff. Jumping into Python with Matplotlib is more familiar for them to help pull them in. So it makes perfect sense to go that first. So
Right. Yes, I think you're right. Yes. Yeah. But of course, Plotly support quite nice interactive plots. So that's very useful if we want to check the data. Yes. Okay.
Okay, yeah, thanks for the presentation. It was very
Yeah, thanks. Thanks a lot.
And I think at this point, I'm going to end the recording, stop recording.
Okay. Yeah.